All right. Good afternoon, everybody. So hopefully you guys are safe and dry this stormy weather. Good afternoon, Bea, Prince, and Trisha. Tapos na-realize ko lang baka never pa ako nakapagpakita sa inyo, no? So that's why I decided to open my camera, at least for the start of the class. So just a couple of reminders first. Naki-canvas na yung problem set number 4, which is the last for the semester. So congrats guys, almost at the end na kayo. So may two problems lang sa problem set. I know I promised there would be three problems, pero binawasan ko na lang siya kasi inisip ko rin na baka marami kayong ginagawa for the ito ng dulo ng semestre. So binawasan ko na lang siya. So two problems na lang siya, naki-canvas na siya. The deadline is on when? December 21st, if I'm not mistaken. And then the details for the final project are also up in Canvas na rin. So the deadline is either January 10 or it could be January 11 depending on when the final exam is scheduled by the registrar. So kung ang schedule ng registrar para sa final exam ng Math 101 would be January 10 or earlier, so ang deadline natin ay magiging January 10. Kung ang deadline ang final exam according kay registrar para sa Math 101 ay January 11, then i-move ko yung deadline ng final term paper papunta sa January 11. So basically, it's either January 10 or the deadline or the schedule set by the registrar, whichever comes later. Okay? Para medyo may dagdag kayong time para gawin yung final problem set. Sorry, yung final term paper. Tapos dun sa problem set, na-realize ko rin na never pa pala tayo nakita-kita, hindi tayo nakapag-turn on ng camera. So I requested you guys in the problem set to sort of show me how you look like para naman kung magbalik man tayo sa face-to-face sa mga susunod na taon is matandaan ko kayo if ever we bump into each other sa math building. So para makilala ko kayo at ma-recognize kayo na isa kayo sa mga naging estudyante ko sa Math 101. So, don't worry, hindi ko naman i-upload kung saan, hindi ko ipapang-blackmail sa inyo yung selfie na ilalagay nyo sa problem set number 4. So, hanggang doon lang siya sa problem set number 4. What else? Okay, also, if you know some of your classmates who are badly affected by the typhoon or the storms, nawalan ng internet, nawalan ng kuryente, or medyo nahirapan, nag-evacuate, hindi nakagawa ng problem set. And if they reach out to you, please relay their message to me and also relate to them na open ako to extend the deadline for their problem sets. So wala naman tayong magagawa and it's not their fault. So please give and extend my assurance to them na we will make proper accommodations for everyone that are badly affected by the typhoon. All right? Kasi kahit ako, ang bagal ng internet ko maghapon, so kinancel ko yung iba kong mga meetings. But I am very happy that we are, na pinagbigyan tayo ng internet connection ko today, that we can meet each other for this last session for this semester. Okay? Oh, by the way, if you have read the problem set already, baka kinabahan kayo about problem 1F, which talks about which asks you to draw a lattice diagram. But that topic requires cardinal numbers, which is the topic that we will discuss today. So, huwag kayong mag-alala. Oops, eto na nga. Yun. Yun na nga, napuputol na yung internet ko na naman. So, yeah, huwag kayong masyadong mag-alala kung medyo or tanggalin niyo yung kaba about problem 1.f kasi ngayon natin siya i-discuss. All right? So, do you guys have any questions or comments, suggestions about the problem set? Kasi otherwise, medyo paspasan yung gagawin kong discussion today, so I apologize in advance. Medyo mabilis to, pero yun nga, kung nakita niyo yung problem set, don't worry about much of the topic today. Hindi sila yung nasa proving part. So this would focus more on the appreciation of the concepts and the terminologies that we will introduce today. All right? So if you don't want to say anything, then let me turn off my camera. At least nakita nyo na ako, may proof of life na ako. So, all right, so let me start sharing my screen and then we can go to the formal discussions. Okay, so for today, we'll be talking about cardinal numbers and basically the concept of infinities, all right? So do you guys see my screen? Medyo delay yata sa laptop ko, but I hope you're seeing it from your end. Kita nyo ba? Nagtatry ako mag-doodle or di lang kinakaya ng internet ko na dalawang devices ng sabay. All right. Pati yung reaction ni Prince, hindi ko na rin nakita pero nakita ko nag-blur yung yung profile pic mo. So, okay. Thank you, Bea. Thank you, Prince, for the reaction. Okay, there we go. I hope I'm back. Um, Kita niyo pa ba guys yung screen ko? Or kailangan ko mag-restart ng screen sharing? Oh, na-disconnect pala ako totally. So hold on. Okay. Nakita niyo pa ba yung hidden message ko dun sa share screen or hindi na? But anyway, as I was saying, today we'll be talking about cardinal numbers and essentially the concept of infinities. Medyo mahirap yung topic because again, I will ask you to forget about the notions of numbers that you know from elementary and college, elementary, high school, and college, like what we did with the set of natural numbers. So napaka-familiar sa atin ng set of natural numbers. Siguro sanay nga lang tayo na nag-start siya kay 1, 2, 3, 4, pero ngayon sinama natin si 0. Pero maganda kasi yung pagkaka-laymanize sa atin ng set of natural numbers na alam natin yung number 0, number 1, number 2, number 3. But all behind this sort of a user interface or layman's interface, yung foundation ng natural numbers, hindi talaga sila mga numbers kasi wala talagang konsepto ng numbers. Sila talaga ay mga sets. Remember, in our formulation of set theory, we did not define the concept of a number. All right? Pumasok lang siya kay Peano's axiom as a shorthand, a convenient shorter way of writing sets. Kasi nga ang natural numbers, sabi natin, sila yung mga miyembro ng minimal successor set, right? Governed by Peano's axioms. So, ibig sabihin, yung wala talagang konsepto ng number, si number 0, siya lang yung shortcut natin pagsusulat sa empty set. Yung number 1, siya lamang yung shorthand natin sa pagsusulat ng set containing the empty set. Si number 2, siya yung shorthand natin para sa set containing the empty set and the set containing the empty set and so on. And these guys are the members of the minimal successor set omega that we know. All right? Tapos yung pagkakaturo sa atin ng addition ay 1 plus 2 ay equal kay 3. All right? But at the back of our minds, hindi siya ganun talaga nagwo-work kasi synthetic yung konsepto ng numbers or napaka-abstract nilang tingnan. At the back end, etong mga numbers, sila talaga ay mga sets. So titingnan natin kung paano sila nade-develop. Pero for today, we'll be talking more about cardinal numbers. Siguro yung mga technical details na yun, titingnan nyo na sa elementary theory of numbers, which is Math 103. But more on cardinal numbers. And cardinal numbers basically describe how big a set is. All right? Gaano kalaki yung isang set. Now, we formally begin the discussion with defining what it takes for two sets to be equivalent to each other. We say by definition one that the set A is equivalent to a set B denoted by A tilde B. So ito yung notion ng equivalence. And this is true if there exists a bijective function from the set A to the set B, right? In other words, kapag may nakita kang one-to-one correspondence, a function or an assignment that is injective and surjective at the same time from a set A to a set B, then we say that the set A, halimbawa, palitan ko na yung color, medyo para ma-highlight siya, ma-differentiate from the text. So halimbawa, meron kang set A, which is the first or the letters in the English alphabet. So hanggang kay Z. And then si set B naman ay numbers 1, 2, 3, 4 hanggang 26. So and then if you will be able to define a one-to-one correspondence, kahit isa lamang na one-to-one correspondence from, then we can say that the two sets are equivalent. Now, of course, there could be several functions that can be defined from the set A to the set B. Pero one such function that you can define is to assign to a letter kung pang ilan siya dun sa alphabetical order o dun sa lexicographic ordering ng English letters. So in other words, we will assign the letter A to the number 1 because it is the first letter in the alphabet. D is mapped to 2, C is mapped to 3, D is mapped to 4, and so on. So here we see that if we proceed in such a manner in assigning elements of A to elements of B, we are sure that there exists no element of B that acts twice as a second element. Ibig sabihin, pag magkaiba yung elements ni A na pinili natin, sure tayo na magkaiba yung elements ni B para sa kanila. So that makes that lexicographic mapping to be one-to-one. And then, of course, for every element of capital B, there is always a pre-image in capital A. Pag pumili tayo halimbawa ng 4, alam ko ang pre-image niya ay si D. Halimbawa, piliin ko si 10, alam ko ang pre-image niya ay si J. And so on. So, ibig sabihin, ang range ng assignment natin ay si B. And since we have a one-to-one, since we have an injective and surjective function between the set A and the set B, we say there is a bijection between A and B. Therefore, by definition 1, they are equivalent to each other. Okay? So what if I say, okay, halimbawa si set B naman ay gawin ko lang 1, 2, 3, 4. Okay? Now, can we define a one-to-one correspondence between A and B? Of course, it's easy to define a surjective map from A to B. Kasi para maging surjective siya, dapat sa bawat element ni B, meron akong i-assign na element ni A. Merong pre-image siya in A. So, halimbawa, pwede kong sabihin si 1, imamap ko kay A. Si B, si 2, imamap ko kay B. Si 3, imamap ko kay C. Si 4, imamap ko kay D. So ang range nung mapping na yon ay set B. So surjective pa rin yung mapping. Ang problema, ang domain niya ay hindi naging si A. Kasi A, B, C, D lang yung nabigyan ko ng function value. So ang domain lang nung bagong function na to na dinefine ko ay set containing A, B, C, and D. Pero di ba gusto natin one-to-one correspondence from A to B. So ibig sabihin dapat lahat ng elements ni A may kapartner na elements ni B. So remember, minap ko na si A kay B, si 2 kay, gamitan ko na ibang color. Si 1, minap ko kay A, si 2, minap ko kay B, si 3, minap ko kay C, si 4, minap ko kay D. Para ngayon magkaroon ng kapartner, yung mga natitirang elements ni A, mapipilitan na akong i-map sila doon sa mga elements ni B na may kapartner na before. For instance, I will be forced to map E to say the same number 4. But doing so will make the mapping hindi na injective. Hindi na magiging one-to-one yung mapping. So that makes the definition or the creation of a one-to-one correspondence between the set A and this set B to be bijective. So walang bijection na kung ma-define from a set A to a set B. So hindi sila equivalent sa isa't isa because no matter how I try, hindi ako makapag-define ng bijective function mula kay set A hanggang kay set B. And probably you will now realize bakit ganon yung ginawa natin to describe equivalence. Sort of in layman's terms, yung equivalence ng dalawang set, ibig sabihin magkasing dami sila ng laman. Right? Now, it can be shown that the relation of equivalence ay isang equivalence relation sa collection of sets. So that is tilde is reflexive, symmetric, and transitive. Dahil napopossess niya yung tatlong properties na yon, equivalence relation siya, tas taglay niya lahat ng properties ng isang equivalence relation. Okay? Now, other terms for equivalent sets, they are equipotent, equipotent, similar, or equinumerous. So medyo obvious siya kung bakit tinawag na equinumerous. Kasi magkasing dami yung mga elements nung set A at saka set B para maging equivalent sila. Now, I don't usually use the term equivalence para dito sa pagkakaroon ng one-to-one correspondence with them. Kasi parang napaka-redundant ng equivalence. Pag sabihin kong equivalence is an equivalence relation, parang ang odd naman pakinggan, di ba? And of course, depending on the context of discussion, being equivalent might have a different connotation to it. So kaya usually ginagamit kong term ay equipotent para dito sa equivalence na to. So all throughout the discussion, if you hear me saying equipotent, siya lang yung equivalence, the existence of a one-to-one correspondence between the two sets. All right? At saka mukhang pang matalino yung equipotent. So pag ginamit mo yung term na equipotent, then parang napaka-highfalutin o napaka-sounding matalino. Kaya siguro siya rin yung gusto kong gamitan. Pero joking aside, yeah, ang dahilan talaga, yung equivalent kasi maraming nakakabit na bias or connotations to it. All right? Now we have seen a nice example of equivalence. So set of all letters from A to Z and the set of all numbers from 1 to 26. Pero meron ding mga iba pang mga sets na interesting yung equivalence nila. Halimbawa, the closed interval 0, 1. Tapos yung closed interval 2 to 5. Now, dahil pwede ako mag-define ng isang one-to-one correspondence, specifically the linear function 3x plus 2. Now, you can check that this guy is a one-to-one correspondence kasi madaling i-prove na one-to-one ang linear functions. If you look at the graph of the line, the graph of any linear function, it is just a straight line. I mean, any linear function, tama nga ba? Lahat ng linear function, straight line lang yung graph niya na non-horizontal, non-vertical, and then it will definitely satisfy the horizontal line test. So lahat ng linear functions ay one-to-one. Tapos, pag kumuha ko ng isang element ni 0, 1, ang function value niya under this linear map ay nasa closed interval 2 to 5. And we can always find the pre-image of any number from the closed interval 2 to 5, and what we will get is a number from 0 to 1. So it can be shown that this function is a one-to-one correspondence between the set G and the set H. And so we can say by definition 1 that the set G is equipotent with the set H. And this is sort of a little bit hard to accept if you will be telling this to a layman. Sabihin mo sa kanya, "Hoy, alam mo ba, yung closed interval 0, 1, kasing dami lang nung laman niya yung set containing 2 to 5, yung closed interval 2 to 5." And then he will say, paano mangyayari yon? Yung closed interval 0, 1, ang length niya ay 1. It's 1 unit long, but the set H, meron siyang length na equal kay 3. And how come that they will have the same number of members? Now, kaya medyo mahirap siyang ipaliwanag. And the thing there is, ito yung problema natin with infinite sets. It's really sometimes hard to wrap our minds around the concept of infinity. All right? Pero later na natin pag-usapan yung infinity. Pero yun nga, ang requirement lang para sa equivalence, pagkakaroon ng one-to-one correspondence. So kung kausap mo si layman na ayaw pumayag na equivalent si G at saka si H, pwede mo siyang sabihan na, okay, bigyan mo ako ng isang element ni G. Bigyan mo ako ng isang number from 0 to 1, tapos makakapagbigay ako sa iyo ng unique na element ni 2 to 5. Tapos kahit ano pang element ni 0, 1 yung ibato mo sa akin, lagi ako makakapagbalik sa iyo ng element ni close interval 2 to 5. Gagamitin ko lang tong formula na to. And for any challenge coming from G that you give me, I can give a response coming from the set H, which is unique for that element of capital G. So hindi kayo matatapos, pero at least hindi ka papatalo na sa pag-argue na equivalent yung dalawang set. Okay? Another example is the set of natural numbers together with the set of positive even integers. So kung isulat natin si n, so 0, 1, 2, 3, 4, 5, and so on. Okay? Tapos, si set of all even natural numbers, we denote it by 2n. Sila lamang yung 0, 2, 4, 6, 8, 10, 12, and so on. And these two sets are actually equivalent with each other. And again, medyo mahihirapan na naman yung mga laymans na tanggapin na bakit sila magiging magkasing dami lamang ng laman. Obviously, si 2n ay proper subset ni n. Kasi lahat ng nakay n, nakay 2n, ay nakay n, pero may mga laman si n na wala kay 2n. For instance, 1, 3, 5, 7, and so on. But it turns out that they are really equivalent to each other kasi yung pairing na pwede natin gawin, which is a one-to-one correspondence, could be mapping 0 to 0, 1 to 2, 2 to 4, 3 to 6, 4 to 8, 5 to 10, and so on. So yun yung magiging mapping. Tapos sasabihin mo sa kanya, sige, bigyan mo ako ng natural number. Bibigyan kita lagi ng unique, even natural number. Tapos hindi uli kayo matatapos. Actually, kung insistent talaga siya, pwede nyo sabihin, pag binigyan mo ako ng natural number n, ang kapartner niya ay 2n. Tapos, yung mapping na yon ay 1-to-1 and onto. So, ibig sabihin, meron akong 1-to-1 correspondence. So, I can conclude that 2n is equivalent with the set of natural numbers. All right? So, is that clear so far? So, medyo nakukumbinsi ko na ba kayo sa notion ng equivalence or equivalence ng dalawang sets? Especially the infinite ones, kasi ito yung medyo mahirap tanggapin at the beginning. All right? Okay. Now, this is another nice example in exercise 5. Okay. In exercise 5, it is claiming that the open interval negative pi over 2 to pi over 2 is equivalent or equivalent to the set R. So, itong open interval na to, na ang haba niya lamang ay pi units. Okay, I hope I'm back. Sorry, na-disconnect na naman ako. So I was saying the open interval negative pi over 2 to pi over 2. It is an open interval of length pi, and yet it is equivalent to the set of all real numbers. So para ma-prove yan, kailangan nyo lang makahanap ng one-to-one correspondence. Define a function on the open interval or from the open interval towards R and show that it is bijective. Now, one such example, pwede niyong itry yung f of x equals tangent of x, where x is from the interval negative pi over 2 to pi over 2. All right? So ito yung pwede niyong gamitin para mapakita na siya ay one-to-one. Remember yung graph ng tangent, graphically madali siya makita kasi kung i-graph mo siya negative pi over 2 to pi over 2, alam natin asymptotic ang tangent dyan. Okay. And then the graph probably will look like this. Okay. Ng tangent. And it will satisfy the horizontal line test from negative pi over 2 to pi over 2, so it is 1 to 1. And then if you look at the range of the function values go down indefinitely, so papuntang negative infinity yan. Tapos pataas din siya ng pataas indefinitely, so papunta siya sa positive infinity. So ang range ng tangent, even if the domain is restricted on the open interval negative pi over 2 to pi over 2 is still R. Okay? So yun yung pwede niyong gamitin para ipakita na equivalent itong open interval na to kay R. Okay? Now, at this point, pwede na nating i-define yung cardinality ng isang set o yung cardinal number ng isang set. And that is in definition 6. We say that the cardinal number or cardinality of A is the equivalence class induced by equivalence having A as a member. So this is consistent with our notion of natural numbers, 'di ba? Ang konsepto ng natin ng natural numbers, hindi talaga sila si 0, 1, 2, 3, 4. Mga symbols lang sila para dun sa mga sets na nasa loob ng set of natural numbers. So, ibig sabihin yung mga numbers pala, dine-develop natin sila as mga sets. So, cardinal numbers, being numbers on their own right, actually are also sets. Specifically, they are the equivalence classes induced by the equivalence relation equivalence. So ang cardinal number ng isang set ay yung set of all sets that is related to capital A via the relation equivalence. So parang kinokolekta lang natin yung cardinal number, siya yung collection ng lahat ng mga sets na equivalent kay capital A. So kung kukunin natin yung cardinal number ni n, denoted by the absolute value of n, right? So ito yung cardinal number ni n. Siya lamang yung equivalence class ng lahat ng mga sets that is equivalent to n. So nandyan yung sarili niya kasi nga reflexive yung relation. Sino pa bang equivalent kay n? O, nakita na natin si 2n ay equivalent kay n. Actually, in general, yung mga multiples ni n ay equivalent sa kanya. So members sila ng equivalence classes. Sino pa ba? Actually, mamaya pwede kong ipakita na si z ay equivalent din kay n. Yung mga rationals, equivalent din siya kay n, and so on. Alright? So ito yung konsepto ng cardinal numbers. Pero again, para mapasimple yung cardinal numbers, pwede natin siyang tingnan as the natural number that is equivalent to the equivalence class. So kung halimbawa, 4 yung laman ng equivalence class, we can write the cardinal number of that set to be equal to 4. Yung parang notation natin, shorthand natin para sa set elements. So medyo technical nga siya, pero don't worry about it. Ito yung foundation. Parang pwede niyong isipin na yung mga numbers, sila yung front end ng program o ito yung user interface. Tapos sa likod ng user interface, yung mga sila ay mga sets. Specifically, yung cardinal number siya ay equivalence class under the equivalence relation. Okay? Now, I will skip a lot of things here. I will, okay. I will skip domination. This is an important thing, equivalence, this is an important theorem about the domination relation, the Schroeder-Bernstein theorem. But I would leave this as a reading assignment for you guys. Wala na rin kasi tayong oras. Pero this is not this is not very important for us right now. So skip ko na lang siya. Hopefully makita niyo yan sa elementary theory of numbers or math 103 later. And then pupuntahan ko na yung transfinite cardinals and countable sets. Now, dito natin i-define ano yung konsepto ng infinity. Though meron na tayong bias, meron na tayong notion kung ano yung infinity. but we haven't defined it yet. Now, we say that a set is infinite if it is equivalent to a proper subset of itself. So yun yung konsepto ng pagiging infinite. Now, we already know examples of infinite sets. Halimbawa si set n. Alam natin infinite yan, or infinite yung dami ng laman niya, because it is equivalent to one of its subsets, specifically 2n, because there is a bijection between n and 2n, all right? And it so happened that 2n is a proper subset of n. So we have shown that n is has a proper subset that is equivalent to it. So ibig sabihin si n ay infinite. Now, si set of integers is also infinite kasi equivalent siya sa set of all natural numbers. So you might be thinking, paano mangyayari na yung set of integers ay magiging equivalent sa set n? So lista natin sila siguro. So si set n, sulat natin 0, 1, 2, 3, 4, and so on. Tapos si integers, the usual way we write integers is dot, dot, dot. So may ellipsis ka muna. Tapos -2, -3, natural order nga pala. -1, 0, 1, 2, 3, dot, dot, dot. All right? So yan yung mga integers. And then if you will attempt to define a one-to-one correspondence between them, we need to be a little bit cunning or a little bit creative with how we do the assignment. Kasi halimbawa, kung i-assign mo lang si 0 kay 0, si 1 kay 1, si 2 kay 2, si 3 kay 3, tapos na yung mga natural numbers, pero hindi pa natin nadadaanan yung mga negative integers. Alright? So yun yung magiging problema natin. Tapos isipin nyo, baka pala hindi sila equivalent sa isa't isa. But remember, it only requires na merong isang one-to-one correspondence. So we need to be a little bit creative in how to define the bijection between n and z. So kailan kong i-reorder yung pagkakasulat ko ng integers? I can write it as 0, -1, 1, -2, 2, -3, 3, and so on. And I hope that you will agree na masusulat ko lahat ng lahat ng integers in this manner. Wala akong makakalimutan. All right? And if I rearrange z this way, the one-to-one correspondence now becomes more obvious. Si 0, mamamap ko kay 0. Si 1, mamamap ko kay -1. Si 2, mamamap ko kay 1. Si 3, mamamap ko kay -2. Si 4, mamamap ko kay 2. Si 5, mamamap kay -3. And I will not run out of natural numbers that can match any integer. And so we can say that n and z are equivalent to each other. And since the set of natural numbers is a proper subset of z, then we say z is also infinite. Okay? Tapos ganun din yung mga rational numbers. Yung mga rational numbers ay equivalent din kay n. Pero mamaya ko ipapakita kung paano. Right? Now, if you have a set that is equivalent to the set of natural numbers, then we say their cardinal number is Aleph 0. Okay? So ang cardinal number ng natural numbers is denoted by Aleph 0. Remember, technically, the cardinal number is the equivalence class containing a set. So ang cardinal number ni n, siya yung equivalence class containing n. Laman niya lahat ng sets na equivalent kay n. Ang notation natin para sa cardinal number ng set of natural numbers, so parang ito yung dami ng laman niya. Ang tawag natin sa kanya ay Aleph 0 or Aleph not or Aleph null. Ito yung problema sa math, no? Parami na ng parami yung alphabets na ginagamit natin. Naubos na natin yung English alphabet. Halos naubos na rin natin yung Greek alphabet. Nasa Hebrew alphabet na tayo ngayon. So Aleph null or Aleph not or Aleph 0, yung cardinal number ng set of all natural numbers. So we can say that the set of integers also has the cardinal number Aleph 0 because The set of integers is equivalent to n, so they belong to the same equivalence class. So Aleph 0 rin yung kanyang cardinality. Okay? Now, some more terminologies. A set is said to be denumerable if it is equivalent to n. So lahat ng mga lahat ng mga sets na equivalent o kasing dami ng laman ng set of all natural numbers, ang tawag natin sa kanila ay denumerable. Okay? Then a set is non-denumerable if it is infinite but is not equivalent to capital N. So an example of a non-denumerable set is the set of irrational numbers. Another one is the set of real numbers. So we will show this later, or bibigyan ko kayo ng idea mamaya kung bakit non-denumerable yung mga sets na yan. Okay? And then it's as if we are in a shortage of terminologies, bibigyan ko pa kayo ng bagong term, countable. A set is countable if it is finite or denumerable. So paano siya ano yung pinagkaiba niya sa definition 4? Pag numerable at saka pag denumerable at saka non-denumerable, mga infinite sets sila. So applicable lang yung definition 4 kapag ka infinite yung sets. Pag meron kang infinite set na equivalent sa n, siya ay denumerable. Kapag ka siya ay infinite, pero mas mataas yung level niya ng infinity kaysa kay n, ang tawag sa kanya ay non-denumerable. Okay? Now, countable siya, ang isang set ay countable kapag ka either siya ay finite or denumerable. And kaya siguro yung ginamit nilang term ay countable kasi kaya natin silang bilangin. Yung mga finite sets, kaya natin silang bilangin, matatapos tayo sa pagbibilang. Pero kung denumerable yung set, kaya natin yung bilangin, parang 0, 1, 2, 3, 4, 5, 6, 7, 8, pero hindi tayo matatapos pagbibilang. But nevertheless, kaya mong bilangin, hindi ka nga lang matatapos. So yun sinasabi nating countable sets. Ang isang set naman ay not countable or uncountable kapag ka non-denumerable siya at saka infinite siya at the same time. So halimbawa yung set of all real numbers. Paano natin bibilangin yung elements na yan? Siguro mag-start tayo kay 0. Ang problema, after 0, sino yung susunod kong bibilangin? Bibilangin ko ba si 1/2? Hindi pwede kasi baka makalimutan ko si 1/4. So, susunod ko ba si 1/4? Hindi rin pwede kasi baka makalimutan ko si 1/8. And so on. Magkakaroon ng ng dalawang real number, may isa pa ring real number. So, I don't know where to go from 0 forward. Hindi katulad ng integers, halimbawa, pwede ako mag-start kay 0, susunod ko si positive 1, susunod ko si negative 1, tapos susunod si positive 2, tapos susunod si negative 1. Mabibilang ko yung mga integers, hindi nga lang ako matatapos. So kaya siya countable. Pero yung mga real numbers, hindi natin kayang bilangan because we cannot devise a nice way on how to write the set of all real numbers in a roster method. So parang obvious siya kasi hindi nga natin siya kayang isulat in a one-to-one correspondence with a set of natural numbers. Okay? Now, siguro mapapaisip kayo, sir, sabi mo kanina ang rationals ay countable or equivalent siya kay n. So, kaya lang, paano ko siya bibilangin? Actually, George Cantor came up with a nice way of counting the rational numbers. Ito yung binigay niya. Okay. Gumawa siya ng table, isang infinite spreadsheet. So, nilagay niya sa column header yung mga possible denominators. Tapos nilagay niya sa row headers lahat ng possible numerators. So, siguro ilagay ko dito si 0. So dito nilagay niya row header divided by the column header. So meron siyang 1/1. Pero para makompleto natin yung mga rationals, lagyan ko to ng plus or minus. Para kasama na si positive 1 at saka si negative 1. Dito naman, sa entry na to, row number 1, yun yung numerator. Denominator is 2. Siya yung nasa denominator. Denominator 2, yung column header yung ginamit ko. So, lagyan ko rin to ng plus or minus 1/2. Tapos, gawin ko to sa lahat. Lagyan ko ng plus or minus. And so on. Tapos, Do you agree na nalista ko na dito lahat ng posibleng rational numbers? Remember, rational numbers are just the ratio of two integers. Any rational number can be written as a natural number over a natural number or an integer over an integer para kasama yung mga negative rational numbers, right? So in this way, I can enumerate all of the rational numbers. Tapos, paano ko siya bibilangin? Kung magbibilang ako ng paganito, mauubos na yung mga natural numbers, hindi pa ako nakakapunta sa second row. O kung gagamitin ko yung assignment na ito yung assign ko kay 0, ito yung i-assign ko kay 1, ito yung i-assign ko kay 2, i-assign ko kay 3, kay 4. Mauubos na yung mga naturals o magagamit ko na lahat ng mga naturals, hindi pa ako nakakapunta dun sa pangalawang row. Pero sabi ni Cantor, bakit ka ganun magbibilang? Hindi ka talaga matatapos. Ganito mo siya bilangin. Mag-start ka kay 0. Tapos, you go diagonally. Susunod mong bilangin ay si positive 1 saka si negative 1. Tapos sunod mong bilangin si positive 2 at saka si negative 2. Tapos susunod si 1/2 saka si negative 1/2. Parang zigzag yung pagbibilang niya. Positive 1/3 saka negative 1/3. Tapos ito, ligtangan mo yan kasi 1 na naman yan. So, pupunta na ako kay plus at saka minus 3, plus and minus 4, plus or minus 3/2, plus or minus 2/3, plus or minus 1/4, and so on. Of course, meron ako mga kailangan ligtangan kasi sila ay mga naulit na, yung mga hindi pa naka-lowest terms. Pero if I will count them diagonally, ibig sabihin hindi ako mauubusan ng natural number na cover ko na lahat ng rational numbers at may sobra pa. So this proves that the set of rationals is equivalent with the set of all natural numbers. Ibig sabihin, yung cardinality ng set of rationals ay Aleph 0. Medyo pangit yung pagsusulat ko ng Aleph 0. Hindi ko natutunan paano magsulat ng Aleph symbol. So this is Aleph 0. So equivalent siya. Ibig sabihin, the numerable ang set Q at siya ay countable at the same time. Okay? So, any questions so far? Okay. Now, siguro daanan ko na rin itong continuum hypothesis. Now, okay. Gusto ko siyang paiksiin na lamang. All right. Okay. Now, I will discuss some things without proof. So kung gusto nyong daanan yung mga proofs niya, reading assignment na lang. But I would like you to think of it as an appreciation discussion for Math 101. So nalaman na natin na si N, may cardinality siya na Aleph 0. Okay. Ganun ko na lang isusulat yung Aleph. Marami kasi siyang pasikot-sikot. So ganito na lang yung Aleph ko. Tapos sabi natin, si irrationals, hindi natin siya kayang isulat as hindi natin siya kayang i-put into one-to-one correspondence with N. So ibig sabihin iba yung cardinality niya than Aleph 0. So it's another level of infinity, right? But how can one produce another level of infinity aside from coming from another infinite set? Actually, it can be shown that the power set of a set A will contain another level of infinity compared to what you already began with. So halimbawa, kukunin ko yung yung power set ng natural numbers, this will give me another level of infinity. So alam ko si n ay infinite, siya yung pinakamababang level ng infinity, Aleph 0 siya. Pag kinuha ko yung power set ni n, tapos binilang ko yung laman ni power set ni n, actually, we have a theorem for this, right? Pero nag-apply lang siya sa mga finite. Ito ay 2 to the power number of elements of capital N. Pero ang number of elements ni capital N ay Aleph 0. Alright? So, ibig sabihin, may theorem, I think it's theorem 6.3 here, okay, na hindi natin i-discuss in details. Ito ay hindi na equal kay Aleph 0. This is equal to another level of infinity, and let's call it Aleph 1. So this guy is not equal to Aleph 0. So ibig sabihin, nakakuha tayo ng isa pang cardinal number na mas malaki kesa kay Aleph 0. Actually, it's not just equal, mas malaki yung Aleph 1 kesa kay Aleph 0. Okay? And then some examples of sets that have cardinality Aleph 1 are the set of irrational numbers, the set of real numbers. All right? Because it can be shown that these sets are equivalent to the power set of capital N. Tapos kung gusto mo mag-create ng another level of infinity aside from Aleph 1 and Aleph 0, kumuha ka lang ng isang set of cardinality Aleph 1. So, halimbawa si R. Kunin mo yung power set ni R. Remember, ang power set ni R ay set lang ng lahat ng subsets ni R. Napakarami nila. Actually, gaano sila karami? 2 to the Aleph 1. And 2 to the Aleph 1 is not equal to Aleph 1. This is another level of infinity. We can call it Aleph 2. And this is definitely greater than or strictly greater than Aleph 1. Okay? Ito yung mga iba't ibang levels ng infinity. Kaya some infinities are larger than other infinities. Okay? Tapos ngayon, may isang interesting question. Alright, sige. Yung Aleph 1, mas malaki kay Aleph 0. Pero meron pa bang infinity sa pagitan ni Aleph 0 at ni Aleph 1? Meron bang Aleph 1 half? Alright? Or in other words, meron bang set na mas marami ang laman kesa kay capital N sa set of natural numbers pero mas kakaunti yung laman niya kesa sa power set ni capital N? So again, is there another cardinal number between Aleph 0 and Aleph 1? The answer, hindi natin alam. Alright, so may butas yung theory natin. And that is to be expected because Gödel said na hindi kung ang axiomatic system mo ay consistent, hindi siya magiging complete. So we need to accept the fact that there are some statements that we cannot prove in a certain axiomatic system. And it so happens that the existence of an infinity between Aleph 1 and Aleph 0 is one of those conundrums that we cannot answer with a Zermelo-Frankel set theory. So, nalalagay yung hypothesis na yan, ang tawag natin sa kanya ay Continuum Hypothesis. The Continuum Hypothesis is claiming that there is no cardinal number beta between Aleph 0 and Aleph 1. Ibig sabihin, pinakamaliit na level na ng infinity si Aleph 0, tapos ang susunod na pinakamababang level ng infinity ay si Aleph 1. Okay? Ang problema, hindi ito kayang i-prove using Zermelo-Frankel set theory. In 1940, ayan, nakalimutan ko na naman yung history ko. I think si George Cantor or si Gödel. Sige, mamaya ko nasasabihin yung history ng Continuum Hypothesis. I-google ko ulit yung Wikipedia page nito. So, I think, yeah, it's Gödel and some other mathematician. Lagi ko nakakalimutan. Pero while I am Googling that, all right? So, is it okay if I borrow 10 or 15 more minutes? Last meeting na naman, guys. Pagbigyan nyo na ako. So, I want to share with you this nice video talking about the levels of infinity. All right? And I think you will like it. So kasi naganda na ako sa kanya ever since nasa YouTube playlist ko na siya. Okay, so let me share my screen. Lipat ako doon. Pakisabihan na lang ako kung walang sound. Hopefully ma-share ko siya with sound. Okay, okay. This one, the TED video by Jeff Defofsky. All right. So let's watch this one.
In the 1920s, the German mathematician David Hilbert devised a famous thought experiment to show us just how hard it is to wrap our minds around the concept of infinity. Imagine a hotel with an infinite number of rooms and a very hard-working night manager. One night, the infinite hotel is completely full, totally booked up with an infinite number of guests. A man walks into the hotel and asks for a room. Rather than turn him down, the night manager decides to make room for him. How? Easy. He asks the guest in room number 1 to move to room 2, the guest in room 2 to move to room 3, and so on. Every guest moves from room number n to room number n plus 1. Since there are an infinite number of rooms, there is a new room for each existing guest. This leaves room 1 open for the new customer. The process can be repeated for any finite number of new guests. If, say, a tour bus unloads 40 new people looking for rooms, then every existing guest just moves from room number n to room number n plus 40, thus opening up the first 40 rooms. But now, an infinitely large bus with a countably infinite number of passengers pulls up to rent rooms. Countably infinite is the key. Now, the infinite bus of infinite passengers perplexes the night manager at first, but he realizes there's a way to place each new person. He asks the guest in room 1 to move to room 2. He then asks the guest in room 2 to move to room 4, the guest in room 3 to move to room 6, and so on. Each current guest moves from room number n to room number 2n, filling up only the infinite even-numbered rooms. By doing this, he has now emptied all of the infinitely many odd-numbered rooms, which are then taken by the people filing off the infinite bus. Everyone's happy, and the hotel's business is booming more than ever. Well, actually, it is booming exactly the same amount as ever, banking an infinite number of dollars a night. Word spreads about this incredible hotel. People pour in from far and wide. One night, the unthinkable happens. The night manager looks outside and sees an infinite line of infinitely large buses, each with a countably infinite number of passengers. What can he do? If he cannot find rooms for them, the hotel will lose out on an infinite amount of money, and he will surely lose his job. Luckily, he remembers that around the year 300 BCE, Euclid proved that there is an infinite quantity of prime numbers. So to accomplish this seemingly impossible task of finding infinite beds for infinite buses of infinite weary travelers, the night manager assigns every current guest to the first prime number, 2, raised to the power of their current room number. So the current occupant of room number 7 goes to room number 2 to the 7th power, which is room 128. The night manager then takes the people on the first of the infinite buses and assigns them to the room number of the next prime, 3, raised to the power of their seat number on the bus. So the person in seat number 7 on the first bus goes to the 7th power, or room number 2187. This continues for all of the first bus. The passengers on the second bus are assigned powers of the next prime, 5. The following bus, powers of 7. Each bus follows powers of 11, powers of 13, powers of 17, etc. Since each of these numbers only has 1 and the natural number powers of their prime number base as factors, there are no overlapping room numbers. All the bus's passengers fan out into rooms using unique room assignment schemes based on unique prime numbers. In this way, the night manager can accommodate every passenger on every bus, although there will be many rooms that go unfilled, like room 6, since 6 is not a power of any prime number. Luckily, his bosses weren't very good in math, so his job is safe. The night manager's strategies are only possible because while the infinite hotel is certainly a logistical nightmare, it only deals with the lowest level of infinity, namely the countable infinity of the natural numbers, 1, 2, 3, 4, and so on. Georg Cantor called this level of infinity Aleph 0. We use natural numbers for the room numbers as well as the seat numbers on the buses. If we were dealing with higher orders of infinity, such as that of the real numbers, these structured strategies would no longer be possible, as we have no way to systematically include every number. The real number infinite hotel has negative number rooms in the basement, fractional rooms, so the guy in room 1/2 always suspects he has less room than the guy in room 1, square root rooms like room radical 2, and room pi, where the guests expect free dessert. What self-respecting night manager would ever want to work there, even for an infinite salary? But over at Hilbert's Infinite Hotel, where there's never any vacancy and always room for more, the scenarios faced by the ever-diligent and maybe too hospitable night manager serve to remind us of just how hard it is for our relatively finite minds to grasp a concept as large as infinity. Maybe you can help tackle these problems after a good night's sleep, but honestly, we might need you to change rooms at 2 a.m.
Okay, so I hope okay yung pagkaka-broadcast ng video. But in case medyo malabo, so pwede ko siyang i-share yung link sa inyo. But it's a nice illustration of uh, how there are different levels of infinity. Yun nga lang dito sa video na to napakita niya na yung mga sets na to ay equivalent kay capital N. And actually, one nice takeaway from it is yung notion halimbawa ng n cross n cross n cross n, an infinite, countably infinite number of times. Kasi kung gusto nyo mag-construct ng susunod na level ng infinity, pag kinuha mo yung cross product ni n with itself, countably infinite number of times, maging equivalent pa rin siya kay capital N. So parang siya yung infinite number of buses with infinite number of guests inside na pagkasya pa rin siya ni hotel manager doon sa Hilbert Hotel. Alright? Now, before we go to the next video, yan, nakita ko na yun sa continuum hypothesis. It was Kurt Gödel who proved in 1940 na hindi na na consistent yung continuum hypothesis with the Zermelo-Frankel set theory. Ibig sabihin, hindi natin kayang i-prove using the ZF axioms na mali yung yung continuum hypothesis, or the negation of the continuum hypothesis cannot be proven as a theorem in Zermelo-Frankel set theory. All right? So, tapos nung 1963, si Paul Cohen naman, ang pinrove naman niya na ay kung consistent ang ZF axiom set theory, hindi provable ang continuum hypothesis. So, nung 1963, which is, if you think about it, it's not too long ago. So, buhay na siguro yung mga parents natin o mga grandparents natin ng mga panahon na yun. Saka pa lang na-prove na hindi provable ang continuum hypothesis under the Zermelo-Frankel set theory. So, the continuum hypothesis is an example ng isang loophole or butas sa set theory. Hindi natin kayang i-prove or i-disprove ang continuum hypothesis using the 9 ZF axioms that we want. So, if we want to prove the continuum hypothesis, kailangan yung umimbento ng sarili nyong set theory. Or, dahil nga napakita ni Gödel na independent ang ZF ni Cohen, na independent ang continuum hypothesis with the ZF axioms, pwede niyong idagdag siya as another assumption sa set theory na pwede niyong i-develop. So pwede niyo siyang gawing axiom kasi hindi siya provable using any of the previous 9 axioms. And the addition of the continuum hypothesis as an axiom in another brand of set theory will radically change the landscape nung mabubuo yung set theory. Okay? Now, probably to end, meron pang isang video na maganda. Ito naman yung nagka-problema yung night manager na kailan siya nagkakaroon ng mga problema sa pag-assign ng mga room numbers sa infinite number of guests. Pero it will start with an alternative way on kung paano mapagkasya yung infinite number of guests in each infinite number of buses. So, ang ginawa dito ni manager number 1, inassign niya sa powers of a prime. So sa sa number theory, ipoprove niya na there are infinitely many prime numbers. So napagkasya niya using power of primes. Etong manager number 2, magbibigay siya ng isang alternative way on how to assign room numbers to all the guests of this infinitely many buses, or countably infinite buses. Tapos may isang case siyang ipapakita na hindi kayang pagkasyahin sa Hilbert Hotel yung isang specific class of guests na darating. So yung nasa second part ng video, yun naman yung ang cardinality ng mga bagong guests na darating ay Aleph 1 na hindi natin kayang ilagay dun sa isang hotel with an Aleph 0 number of rooms, right? So, tingnan natin itong isa pang video na to. Nasaan na ba siya? Okay. So, ito yung Wikipedia na binabasa ko kanina habang nagvi-video. So, let's play this one.
And then, all of a sudden, more infinite buses show up. Not just 1 or 2, but an infinite number of infinite buses. So, what can you do? Well, you pull out an infinite spreadsheet, of course. You make a row for each bus, bus 1, bus 2, bus 3, and so on, and a row at the top for all the people who are already in the hotel. The columns are for the position each person occupies. So you've got hotel room 1, hotel room 2, hotel room 3, etc. And then bus 1, seat 1, bus 1, seat 2, bus 1, seat 3, and so on. So each person gets a unique identifier, which is a combination of their vehicle and their position in it. So how do you assign the rooms? We'll start in the top left corner and draw a line that zigzags back and forth across the spreadsheet, going over each unique ID exactly once. Then imagine you pull on the opposite ends of this line, straightening it out. So we've gone from an infinite by infinite grid to a single infinite line. It's then pretty simple just to line up each person on that line with a unique room in the hotel. So everyone fits, no problem. But now a big bus pulls up, an infinite party bus with no seats. Instead, everyone on board is identified by their unique name, which is kind of strange. So their names all consist of only two letters, A and B, but each name is infinitely long. So someone is named A, B, B, A, 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 and so on forever. Someone else is named A, B, A, B, A, B, A, B, A, B, etc. On this bus, there's a person with
Okay, excuse me guys. Ito yung isang example na parang equivalent siya sa set of all irrational numbers. So, medyo kakaiba nga lang yung example na to kasi dito ay posible yung mga repeating decimals. So, pwede yung isipin yung mga letters, sila yung numbers after the decimal digits. Pero pagka kasi pag irrational yung number, ibig sabihin non-repeating, non-terminating yung mga decimal representation nila. Alright? So parang ganito rin yung magiging argument para ipakita na yung set of all irrational numbers ay hindi equivalent or hindi equivalent sa set of natural numbers. Mas simple nga to kasi dalawa lang yung character sa bawat position. It's either an A or a B. Sa irrationals naman, sa kanilang decimal representation, sa bawat position, meron kang 10 options. Either starting from a number from 0 until 9, tapos non-repeating, non-terminating yung process. So dun sa proof ng irrational sa vortex, pero ganito yung idea. All right? So let me hit play again. Continue na.
with every possible infinite sequence of these two letters. Now, A, B, B, A, 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 I'll call him ABBA for short. He comes into the hotel to arrange the rooms, but you tell him, sorry, there's no way we can fit all of you in the hotel. And he's like, what do you mean? There's an infinite number of us, and you have an infinite number of rooms. Why won't this work? So you show him. You pull out your infinite spreadsheet again and start assigning rooms to people on the bus. So you have room 1, assign it to ABBA, and then room 2 to AB, 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 AB repeating, and you keep going, putting a different string of A's and B's beside each room number. Now here's the problem, you tell ABBA. Let's say we have a complete infinite list. I can still write down the name of a person who doesn't yet have a room. The way you do it is you take the first letter of the first name and flip it from an A to a B. Then take the second letter of the second name and flip it from a B to an A. And you keep doing this all the way down the list, and the name you write down is guaranteed to appear nowhere on that list because it won't match the first letter of the first name or the second letter of the second name or the third letter of the third name. It will be different from every name on the list by at least one character, the letter on the diagonal. The number of rooms in the Hilbert Hotel is infinite, sure, but it is countably infinite, meaning there are as many rooms as there are positive integers 1 to infinity. By contrast, the number of people on the bus is uncountably infinite. If you try to match up each one with an integer, you will still have people left over. Some infinities are bigger than others. So there's a limit to the people that you can fit in the Hilbert Hotel. This is mind-blowing enough, but what's even crazier is that the discovery of different sized infinities sparked a line of inquiry that led directly to the invention of the device you're watching this on right now. But that's a story for another time.
All right, so yeah, I hope you enjoyed those two videos, and I guess they are nice conclusions to the course. So, and that's the end of Math 101 for this for you guys. Congratulations, tapos na. So, pero may dalawa pa kayong utang sa akin. Kailangan yung i-submit yung problem set number 4 at saka final project. Then once you submitted them, yeah, you will see your final grading since the semester is nearing the end. So please double check the entries in Canvas. So make sure na lahat ng pinasa nyo ay may grade na kay Canvas kasi yung final grade nyo, titingnan lang namin kay Canvas. So whatever is on Canvas, that's going to be your final grade. So for those who had some troubles accessing Canvas during submissions, so tapos napilitan kayo mag-submit via email or via chat sa akin or sa lab instructor nyo, make sure that your score there is also recorded in Canvas. So kung hindi pa siya recorded kay Canvas, pakisabihan kami para ma-record namin kasi yun talaga yung pagbabasihan namin. Wala na kaming separate record aside from that in Canvas. All right? And so to end, it was very nice having you as my student. So I didn't expect Math 101 to be this fun. So thank you for making it an enjoyable experience for me. Hopefully it was also enjoyable for you guys. I really loved the interaction we had for most of the semester, though unfortunately, and I apologize for it, medyo kailangan kong habulin sa dulo yung pacing. Kaya hindi na tayo masyadong nagkaroon ng recitation. But probably in the future, we can suggest na mas mahaba na lang sana yung lecture time. Kunin natin yung content from the lab times. But yeah, that's another administrative thing to consider. Pero yeah, I hope you had fun. You got something from the course. Huwag niyong kalimutan yan kasi gagamitin yan sa mga major courses nyo. Tapos, sige, ayokong makarinig ng reklamo mula sa mga major teachers na, sino bang teacher nyo ng 101? Di nyo natutunan yung method of proof. So, sige, ipagkakanulo ko kayo. Joke lang. Pero yeah, I hope you had fun. And then, of course, we'll see each other around. Hopefully, you stick in the math program. And if you do so, in the Math Applied Math or MST program, and if you do so, siguro magkikita-kita tayo in other courses in the future. So, this is goodbye for now, but hopefully we'll see each other around either in other major courses or we bump into each other sa math building. All right. Bye, everyone. Keep safe, keep dry, and yeah, see you around. Bye-bye.
Thank you po, sir.